When people say threat intelligence, beginners often imagine a single magical artifact, a list of bad things that you block, and then you are safe. In real security work, and especially in operational technology, OT, threat intelligence is more like a toolbox of different data types that each answer different questions. Some intelligence data tells you what to look for, some tells you how to share what you know, and some helps you recognize patterns in files or behaviors. The trick is learning how to use each type without forcing it into the wrong job. In OT, this matters because you are balancing security with safety and uptime, so you cannot treat every signal as a reason to slam the brakes. You need to know what kind of intelligence you are dealing with, how reliable it is, and what action it should trigger in an operational environment. In this lesson, we will focus on 3 frequently mentioned intelligence data types and standards: indicators of compromise, IOCs, structured threat information expression, STIX, and YARA rules. And we will build an intuitive sense of where each fits in OT so you can use them thoughtfully rather than mechanically. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. Indicators of compromise, IOCs, are the most common starting point because they feel concrete, like fingerprints left behind by an attacker. An IOC could be a suspicious domain name, an IP address, a file hash, a registry path, a process name, or a specific command pattern, depending on the environment. The core idea is simple. If you see this thing, it might mean the same attacker or malware is present. For beginners, the biggest misconception is thinking that IOCs are timeless truths, when in reality many are fragile. A domain can change, an IP address can be reused, and malware authors can modify a file to change its hash. Even worse, an IOC can be present for a benign reason, like shared hosting or a reused cloud service address, which creates false positives. In OT, false positives have a higher cost because unnecessary blocking or shutdown actions can interrupt critical operations. So operationalizing IOCs means treating them as hints that guide investigation and monitoring, not as automatic proof of compromise. The first question is always how the IOC was observed and how confident the source is. To use IOCs well in OT, you also need to match the IOC type to what you can realistically see in the environment. Many OT segments do not have full endpoint visibility, and some devices are not instrumented like modern workstations. That means an IP address or domain might be more useful in network monitoring, while a file hash might only be useful on a limited set of systems like engineering workstations, jump hosts, or servers that interface between IT and OT. Another key beginner lesson is that not all IOCs are equal. Some are high confidence and specific, while others are broad and noisy. A unique file hash from a known malware sample can be strong, but only if you have the capability to check it safely on the systems you care about. A commonly used hosting IP might be weak and cause disruption if blocked without context. In OT, you often operationalize IOCs by placing them into a process. Monitor first, validate, then decide on action that does not create unsafe conditions. When you do take action, you want it to be proportional and reversible because the goal is to reduce risk without breaking operations. It is also important to understand the life cycle of an IOC because intelligence is perishable. Some indicators are short-lived, like command and control infrastructure that attackers abandon quickly, while others can persist, like code patterns that show up in multiple variants. Operationalizing IOCs means you have a method to ingest them, evaluate them, apply them where appropriate, and retire them when they are no longer useful. Beginners sometimes treat IOC lists as trophies that grow forever, but that creates clutter, false alarms, and wasted effort. In OT, a cluttered detection environment can lead to alert fatigue, and alert fatigue can be dangerous because the important signals get ignored. A better approach is to curate. Prioritize indicators that are relevant to your industry, your region, your vendors, and your architecture. You also want to store context with the IOC, such as when it was first seen, what incident it relates to, and what confidence level is associated with it. The intelligence becomes more valuable when it is connected to a narrative rather than existing as an isolated string. Structured Threat Information Expression, STIX, is different from IOCs because it is not a specific indicator. It is a standardized way to represent and share threat intelligence in a structured format. Think of STIX as a language for describing what you know about threats, including indicators, malware, threat actors, tactics, techniques, relationships, and sightings. The value of that structure is that it allows different tools and organizations to exchange intelligence in a more consistent way than a random spreadsheet or an email. For beginners, it helps to see that STIX is about packaging context, not just passing around lists. If you share a domain as an IOC without context, the receiver might block it immediately and break something. If you share it in a structured way that includes confidence, time window, and related behaviors, the receiver can make a better decision. In OT, that context is crucial because the same indicator might have different implications depending on whether it touches the corporate network, the remote access zone, or a safety-related engineering workstation. STIX supports that richer story. When you operationalize STIX in an organization, the focus is usually on integration and consistency, not on manually reading the format. Most humans do not sit and parse STIX objects line by line. Tools and platforms consume it. What matters for learners is understanding what you gain and what you risk when you adopt structured sharing. You gain speed, repeatability, and the ability to connect pieces of intelligence into a graph of relationships, which can support better analysis and correlation. You also gain the ability to filter intelligence based on relevance, such as only pulling intelligence related to certain sectors or techniques. The risks include information overload and the temptation to automatically enforce everything without validation. In OT, an automatic block based on shared intelligence can be dangerous if it disrupts vendor support connections or critical communications, so structured sharing must be paired with safe operational controls. The right posture is to use STIX-fed intelligence to inform monitoring and investigation, and then to apply enforcement carefully where you know it will not cause operational harm. The structure helps you manage that discipline by keeping the why attached to the what. YARA is another term that shows up often in intelligence discussions, and it is best understood as a way to describe patterns in files so you can identify malware or suspicious artifacts. A YARA rule is essentially a set of conditions that match certain strings, byte patterns, or characteristics, and it is used to scan files or memory to find things that resemble known malicious code. For beginners, it helps to think of YARA as a pattern-matching recipe that can catch families of malware even if individual file hashes change. That makes it more flexible than a simple hash-based IOC. However, it also requires careful construction and testing because overly broad rules can produce false positives, and false positives can create chaos if they trigger aggressive responses. In OT, YARA is most likely to be relevant on systems that handle files and software, such as engineering workstations, Windows servers used for historians or management functions, and jump hosts used for remote access. It is less relevant on simple embedded devices that do not store files in a way you can scan with the same tooling. So where YARA fits in OT depends on where you have file-based visibility and where scanning is safe and permitted. Operationalizing YARA in an OT environment also requires an appreciation of safety and performance constraints. Scanning can consume resources, and some systems in OT are sensitive to performance disruption or unexpected activity. That is why the where question matters as much as the what question. You might choose to scan in staging areas where updates are validated before being deployed, or on jump hosts where files pass through, rather than scanning directly on controllers or critical process systems. Another beginner lesson is that YARA is often part of a layered detection strategy, not the whole strategy. A YARA match can tell you that a suspicious artifact resembles known malware, which can trigger deeper investigation, but it does not automatically tell you how the malware entered or what it did. In other words, YARA can be a strong signal about capability, but you still need network and log context to understand the intrusion story. In OT, that story often involves remote access, removable media, or IT to OT pivoting. so file detection should be connected to those vectors. YARA is powerful when it is integrated into an investigative workflow rather than treated as a standalone alarm. Now that we have the three pieces, the most useful beginner skill is learning how to place each one in the right layer of an intelligence-driven defense. IOCs are often tactical and immediate, helping you search for known bad infrastructure or artifacts and detect reuse. STIX is a structured way to share and relate intelligence, helping you preserve context and integrate feeds without losing meaning. YARA rules are a way to detect malware families or suspicious file traits beyond simple hashes, particularly in environments where attackers modify binaries. In an OT setting, these tools must be shaped by what you can observe and what you can safely act upon. You might use IOCs to tune network monitoring in the boundary zone between IT and OT, watching for unusual outbound connections or known malicious infrastructure. You might use STIX to ingest intelligence from trusted sources and keep it organized, filtering to what matches your sector and technology mix. You might use YARA in a controlled environment to scan incoming files, engineering project archives, or systems that are likely touchpoints for malicious payloads. The goal is not to deploy everything everywhere, but to be deliberate and realistic. It is also important to discuss the concept of confidence and context explicitly, because intelligence data types can create a false sense of certainty. An IOC might be accurate but outdated. A STIX package might be well-structured but based on limited evidence. A YARA rule might match something benign if the rule is too generic. In OT, the cost of acting on bad intelligence is higher because it can interrupt operations or cause unsafe states. That is why operationalizing intelligence includes validation steps and a decision framework for actions. A common safe approach is to start with monitoring and correlation, then escalate to investigation, then decide on enforcement or containment when you have enough evidence and a plan that respects operational priorities. Another key idea is to attach intelligence to assets and zones, meaning you decide where an indicator matters. A suspicious domain might matter on a jump host that should never browse the internet, but not matter on a corporate workstation that is expected to talk to many domains. When you apply intelligence with asset context, you reduce noise and increase usefulness. In many OT organizations, intelligence becomes most valuable when it helps answer specific operational questions rather than abstract ones. For example, instead of asking, "Are we exposed to this malware?" you ask, "Do any of our engineering workstations show signs of this malware family? And if so, can we verify controller logic integrity before continuing operation?" Instead of asking, "Do we have these IOCs?" you ask, "Do we see any of these indicators in the remote access zone? And do they correlate with unusual session timing or privilege use?" Instead of asking, "Can we consume STIX?" you ask, "Can we share what we learned from an event in a format that other teams can use without misinterpreting it?" These questions point to outcomes, and outcomes drive better intelligence practice. Beginners sometimes get stuck in collection for collection's sake, but the point is decision support. In OT, decision support often centers on safe operation, integrity verification, and minimizing downtime, which is why intelligence must be mapped to operational realities. The final piece is to recognize that intelligence data types are most effective when they are woven into a repeatable process that respects OT constraints. You ingest intelligence, you triage it for relevance, you apply it to monitoring where safe, you investigate hits with context, and you choose actions that reduce risk without creating unsafe disruption. IOCs, STIX, and YARA each play a role in that loop, but none of them are a silver bullet. The biggest mistake beginners make is treating intelligence as something you buy or download rather than something you practice and refine. In OT, the best intelligence practice is often local. Understanding your own environment, your own normal patterns, and your own dependencies, and then using external intelligence to sharpen that understanding. When you approach these data types with that mindset, you stop chasing lists and start building a capability, the ability to see signals, interpret them, and act safely. That capability is what ultimately makes intelligence operational in OT, and it is one of the most practical skills you can develop at the start of your journey.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.